Okay, this is Chapter 8 review. Chapter 8 starts off with percent yield. Percent yield is how much you actually get from an experiment versus how much you expected or calculated that you would get, times 100%. So if you expected 5 grams from an experiment and you only got 4.5 grams, this would be your percent yield. Okay? There's a couple of questions in the review about percent yield. We'll do number 4 real quick. So number 4 is a student heats calcium carbonate to produce calcium oxide according to the following equation. So calcium carbonate is heated to produce calcium oxide and carbon dioxide gas. The student starts with 100 grams and makes 45 grams. What is the percent yield? Well, first we need to figure out what our expected yield is. So if we start with 100 grams of calcium carbonate, we can convert that to moles using the periodic table and the molar mass. 100.09 grams are in 1 mole of calcium carbonate. So we have 0.9991 moles of calcium carbonate. Now it's a 1-to-1, 1 mole of calcium carbonate makes 1 mole of calcium oxide. So we have the same number of moles of calcium oxide. Now let's convert to grams. There are 56.08 grams per 1 mole of calcium oxide. So that is 56.03 grams that we expect to get of calcium oxide. Now we can calculate our percent yield. We got 45.0 grams. We expected 56.03 grams times 100%. If you do this on your calculator, you will get 80.3%. That is our percent yield. We did this in a lab, so hopefully you remember doing that. Number 5 does this, but in the opposite way. Instead of figuring out your percent yield, it gives you the percent yield, and then you plug in, I think you saw for the actual yield. If you need help, text me, email me, and let me know, and we can go through that one later. Okay, so that's percent yield. How do you improve your percent yield in an experiment? You can repeat the experiment, so doing it over and over again. Hopefully you can get better in your technique and get a better percent yield. And just being really careful in the lab. Improving your technique, you can improve your percent yield. The next topic is empirical, which means experimental versus molecular formulas. And if you take Latin with me, you know that the plural of formula is formulae, first declension feminine. So an empirical is kind of like a rounded down formula. It's the base ratio of atoms to each other within a molecular formula. So it's the simplest ratio. So it's just a ratio of, say, carbon to hydrogen in a molecule, whereas the molecular formula is the actual number of atoms in that formula. Carbohydrates all have the base empirical formula of CH2O. That's where they get their name, carbohydrate, carbon, water. So if you see something that has this as its empirical formula, you know it is a carbohydrate. So we can scale this up. Let's multiply it by 4, say. C4H8O4. This would be a carbohydrate. Let's multiply it by 6. C6H12 O6. This would be a carbohydrate. This is glucose. C12, H24, O12. Anytime you see C, H, and O in these ratios to each other, and you kind of reduce the fraction to this empirical formula, you know you're dealing with a carbohydrate. What about ionic compounds? So what is an ionic compound? It's a nonmetal and a metal bonded together. So something like sodium, which is a metal, and chloride, a nonmetal. Potassium and chloride, magnesium and fluoride. It's a metal and a nonmetal bonded together. And remember, in an ionic compound, there's a complete transfer of the electron. So the electron will go from the valence shell of sodium completely over to the chloride, causing a complete charge, not a partial charge like we have in covalent compounds, but a complete plus on the sodium since it's lost its electron, and a complete minus on the chloride since it's gained an electron. I'm going fast because this is all review, hopefully. So, ionic compounds, their empirical formulas are always equal to their molecular formulas. Okay, so anytime you have an ionic compound of a metal and a nonmetal, their empirical formula is going to be equal to their molecular formula. Now, how do you, hold on, let me go through. So numbers 6 and 7 you should be able to do in the review. Let's do number 10 in the review. It has to do with empirical formulas. So number 10 in the review says, a compound has an empirical formula of C3, H7NO. And its molar mass is 146.22 grams. What is its molecular formula? Okay. Well, let's figure out how much this empirical formula weighs. So C3 means it's 3 carbons, which weigh 12.01. H7 is 7 hydrogens, which weigh 1.01. Nitrogen weighs 14.01, and oxygen weighs 16. So this empirical formula weighs 73.11 AMU, right? Each molecule of this weighs 73.11, scaling up to moles. 1 mole weighs 73.11 grams. But 1 molecule, so this is how much its empirical formula weighs. How much does its molecular formula weigh? 1 molecule weighs this much. So we have to figure out what ratio by dividing the molecular mass by the empirical mass. And this is 2. So we know that there's 2, and multiply this whole empirical formula by 2 to get its actual molecular formula. So that will be 2 times 3, C6, 2 times 7, H14, 2 times 1, and 2 times 1. So it will be C6, H14, N2O2. All right. Moving along, how do we determine empirical formulas? Basically by burning things. So you burn a chemical, collect the products, and weigh them, and that will give you the ratio of different elements to each other. So, in review number 11, if you burn a sample of nitrogen with oxygen, the result is a single gas with a certain mass. What is the empirical formula? So this is number 11. A 15-gram sample of nitrogen. You burn it in the presence of oxygen, and you get a gas whose weight is 49.3 grams. So this mass is greater than this mass, so obviously we've picked something up along the way. The only thing we could have picked up to make this gas heavier is oxygen. So the two elements we have over here are nitrogen and oxygen making this gas. And according to the conservation of mass, we can figure out how much oxygen we picked up simply by subtracting. So 34.3 grams of oxygen. Okay, so that's the law of the conservation of mass. That gave us the weight of the mass of the oxygen. Now let's figure out how many moles we have. So 15 grams of nitrogen is, if we divide by 14.01, 1.07 moles of nitrogen. And how much oxygen? 34.3 grams of oxygen is how many moles? Divide by 16, 2.14 moles of oxygen. Now, why aren't we using the homonuclear diatomics? Nitrogen, as you know, is a gas. It's N2. Oxygen is also a gas, O2. They're both homonuclear diatomics. They bond to each other to make an O2 molecule and an N2 molecule. But when we are doing empirical formulas, we're looking for the simplest ratio of atoms to each other. So this is pretty much the only time we're going to use just straight up N and not N2, and just O, not O2. It's because it's an empirical formula. So now we know how many moles we have of each. Let's find the ratio. And it's obvious the ratio is 2. So we have, for every one nitrogen, we have 2 oxygens. So the empirical formula is going to be NO2. Okay? So that's burning something with just one atom and figuring out its empirical formula. What if you have more than one atom in a compound? A more complicated combustion analysis. So what if you're burning a hydrocarbon or a carbohydrate? So hydrocarbon just has hydrogen and carbon, and a carbohydrate has, like we said, CH2O, carbon, hydrogen, and oxygen. You can burn it, whatever your sample is here, in a closed system, so this is fire, and collect the products. So the apparatus looks something like this. You pipe oxygen into the system to give it what's needed for combustion. You burn this completely. In here is something that absorbs carbon dioxide, and in here is something that absorbs water. And then the excess oxygen leaves. So you weigh what's in this chamber and weigh what's in this chamber, subtract whatever your substrate is in there, to get the weight of the carbon dioxide and the weight of the water. Okay? When you get the weight of the carbon dioxide, you can figure out how many moles of carbon dioxide you have, and that will tell you how many moles of carbon you have in your original sample. Same over here, you figure out how many moles of hydrogen you have, and there's 2 here, so you'll have, you just multiply by 2 to figure out how much hydrogen you have in your original sample. And then whatever weight is left over is oxygen. So we'll do a, let me write that real quick. So however many moles of hydrogen you have will give you how many moles of hydrogen you have in your original sample times 2, since it's H2O. However many moles of carbon dioxide you have will give you how many moles of carbon you have in your original sample. And then whatever leftover mass there is attributed to oxygen. Okay, so we'll do number 13 to figure out how to use this. So in chapter 8, review number 13. A 200-gram sample of an unknown substance was burned in excess oxygen to produce 439.3 grams of carbon dioxide and 239.9 grams of water. Okay, so we had 200 grams of something burned in excess oxygen. That just tells us that's not the limiting reagent. And we produced 439 grams of carbon dioxide plus 239.9 grams of water. So what is the chemical formula, molecular formula of what we burned? First, let's figure out how many moles of carbon dioxide we have. So 439.3 grams of carbon dioxide, figure out its molar mass, 44.01. To figure out how many moles there are, we have 9.982 moles of carbon dioxide. So we know that there are 9.982 moles of carbon in our original sample. Now we do the same with the water. 239.9 grams of water is equal to 13.31 moles of water. And since there's two hydrogens here, we're going to multiply this by 2 to get 26.62 moles of hydrogen in our original sample. So now we know how many moles we have of carbon and hydrogen in our original sample. Let's convert those back to grams. So 9.982, just right over here, 9.982 moles of carbon is equal to 119.9 grams of carbon. So that's how many grams of carbon are in this original sample. Same with the hydrogen, 26.89 grams of hydrogen. Okay, so we've got 119.9 plus 26.89, that doesn't add up to 200 grams. So whatever's left, when we add those two together and subtract from 200, is attributed to oxygen, which we got from here. No, I'm sorry, we didn't get it. This is what we use for combustion. It's what's left as oxygen in the original sample. So what's left, if we add these together and subtract it from 200, what's left is 53.2 grams of oxygen. And then we figure out how many moles of oxygen that is by dividing by 16, that's 3.325 moles of oxygen. Okay, so now we know the ratios of carbon to hydrogen to oxygen in our original sample. So we've got 26.62 moles of hydrogen. Let's divide that by our moles of oxygen, 3.325 moles, to figure out their ratio. That is 8. So we've got 8 moles of hydrogen per moles of oxygen. Now let's do the same with the carbon. 9.982 moles carbon divided by 3.325 moles oxygen, and that is 3 moles of carbon per moles of oxygen, or 1 mole of oxygen. So now we can figure out our molecular formula. For every 1 mole of oxygen, we've got 8 moles of hydrogen and 3 moles of carbon. So this is our empirical formula, C3H8O. Okay, but we're not done. The problem tells us that the molar mass of one molecule is 180.33 grams. So now let's figure out what we need to multiply this by to get to this molar mass and figure out our molecular formula. So one of these guys, if you did look up in the periodic table what these weights are, one of these guys weighs 60.11. Okay, so all we need to do now is divide this, and the answer is 3. So we need to know we need to multiply this whole empirical formula by 3. So C3 times 3 is C9, H8 times 3 would be H24, and O times 3 is O3. So our molecular formula is C9 H2403. Is that clear? Is that too fast?